All right, lesson 2.6 and 2.7 should be mostly review of absolute value. So remember that absolute value is a distance from 0 on a number line. So when we're talking about the absolute value of 5, we're talking about how far away is 5 from 0 on a number line. So the absolute value of 5 is 5. The same for negative 5, how far away is negative 5 from 0 on the number line, has a distance of 5, so the absolute value of negative 5 is 5. The new way of thinking about this is that instead of looking at the absolute value of a number, now we can take the absolute value of a variable and we can say that variable must have certain values if its distance away from 0 is 5. So what are the possible values of x? Well, if we look at a number line, and here's 0, and we're looking, good morning, a distance of 5 away is at 5, and a distance of 5 away is negative 5. So we can generalize that for any value a, x can be a or negative a. So there are always up to 2 solutions. Let's look at some examples. The first step for solving these absolute value equations is to make sure that the absolute value is by itself, and then we split it into its 2 cases. The 2 cases are with a positive or a negative solution. So we can say that x over 2 minus 1 is 11, or x over 2 minus 1 is negative 11. And then we solve these 2 equations separately. Now remember, or means that the answer could be one or the other. So when we solve this, add 1 to both sides, x over 2 is 12, multiply by 2 on both sides, then x is 24, or, and then we solve the other side to find that x could be 24 or negative 20. So since we have 2 different solutions, we can write our solution set x is either negative 20 or 24. In this example, we have to isolate our absolute value first. So isolate the absolute value first, subtract 5 from both sides. Then we get the absolute value of 2x equals 2. Notice we have not split into our 2 cases yet, so the absolute value bars are still there. Now when we split into our 2 cases, our absolute value bars go away. So we have 2x equals 2 or 2x equals negative 2. Solving each equation separately, divide by 2, so x equals 1, or divide by 2, x equals negative 1, giving us the solution set x equals negative 1 or 1. Similarly, in example 3, we have our absolute value bar isolated, so we split into our 2 cases, y equals 0 or y equals negative 0, but negative 0 is just 0, so we have one solution where y equals 0. Notice we don't have 2 solutions this time. In the next example, we have to isolate our absolute values again, so subtract 25 from each side. We have 2 times the absolute value of x equals negative 2. Divide by 2, still to isolate our absolute values. So I get that the absolute value of x equals negative 1. But remember, absolute value is a distance. So can I have a distance of negative 1? No. So our answer is the empty set. Anytime you have an absolute value equal to a negative value, you'll have an empty set as your solution. Okay, moving down to the next example. Here, even though we have 2 sets of absolute value bars, since they're each isolated, we can still split it into our 2 cases. So our first case, we'll just take both sides as being positive. X minus 3 equals 5 minus x. For our second case, we choose one side to make negative. If we make both sides negative, we'll end up in the same case as if both sides are positive. So I usually choose the second side. X minus 3 equals negative the whole side, 5 minus x in parentheses. From here, we're solving the equation. So plus 3 plus x plus 3 plus x. We have 2x plus 0 equals 8 plus 0. Divide by 2, x equals 4, or, now we have to distribute the negative here, so we have x minus 3 equals negative 5 plus x. Again, isolating x, so minus x, we have negative 3 equals negative 5, which is false. So from this side we get no solution, but since we have a 4 or no solution, we still have that x can equal 4. So our solution, even though one side was no solution, still includes 4. Okay, on your own, complete this concept check, true or false. Absolute value equations always have two solutions. Okay, the second part to solving absolute values is inequalities. And the thing to remember here is the than and great or, less than and great or kind of trick, which means that if I have an absolute value of x is less than a, it splits into the two cases, x is less than a and x is greater than negative a. Think about a distance being less than a is all of the distances between two numbers. So it's an and. Whereas if I have the absolute value of x is greater than a, that splits into the cases x is greater than a or x is less than negative a. Okay, so if it's a less than, it's an and statement. If it's a greater, it's an or statement. Let's look at some examples. In example 2, we want to solve and graph. We're going to solve, again, to isolate the absolute value, so minus 1 on both sides. Absolute value of 5x plus 1 is less than or equal to 9. And then we split into our two cases. So our two cases, again, it's a less than, so I'm going to put an and symbol. Now, less than, you would just put an or equal to on any of these if it has the or equal to in your symbol. So we have 5x plus 1 is less than or equal to 9. And then 5x plus 1, now because the 9 is changing symbols, we have to change our inequality sign. Greater than or equal to negative 9. I'm going to scoot down here a little bit. Solving each of these inequalities now, minus 1, minus 1. 5x is less than or equal to 8. Divide by 5. X is less than or equal to 8/5. Remember, this is an and statement. Minus 1, minus 1. 5x is greater than or equal to negative 10. Divide by 5. X is greater than or equal to negative 2. So I'm going to rewrite that up here. X is less than or equal to 8/5 and x is greater than or equal to negative 2. So remember what we were doing in the previous sections. If we have our number line here, here's negative 2, here's 8/5. X is less than or equal to 8/5 would be something like this. X is greater than or equal to negative 2 is like this. Where do they and overlap between negative 2 and 8? So on my number line, 8/5. So on my number line, here's negative 2, here's 8/5, and our solution set is between our two values. All right, looking at the examples on the back, our next example we're looking at an absolute value is less than negative 13. Now if we think about this logically, we can say absolute value, remember, is distance. Can I have a distance less than negative 13? No, so it's the empty set. But let's say we don't recognize that. Then we solve this, we break it into our two cases. It's a less than, so it's an and. So we have that 2x minus 1 over 10 is less than negative 13, and 2x minus 1 over 10 is greater than 13. Okay, so we can continue to solve this, multiply by 10 across, so 20x minus 1 is less than negative 130. Add 1, 20x is less than negative 129. X is less than negative 129 over 20. Okay, and 2x minus 1/10. So again, multiply through by 10. 20x minus 1 is greater than 130 plus 1. 20x is greater than 131. Divide by 20. X is greater than 131 over 20. So if we were to graph this, I have here negative 129 over 20 Here, 131 over 20. X is less than this one and greater than this one. Where do they overlap? No overlap. So we get, again, empty set. In the next example, we're looking at a distance less than or equal to 0. So we can have distances equal to 0, but not a distance less than 0. That tells me, logically, that I'm going to have one answer. Let's look at these two cases. So a less than tells me this is going to be an and. So I have 2 times x plus 1 over 3 less than or equal to 0. And then our second case, 2 times x plus 1 over 3. The 0 is becoming negative, so I switch my sign. Greater than or equal to negative 0. Remember, that's my two cases because it's an absolute value. Looking at my first inequality, I multiply by 3 on both sides. 3 over 3 cancels out. So I have 2 times x plus 1 less than or equal to 0. I'll divide by 2. So I have x plus 1 is less than or equal to 0 divided by 2, which is 0. Minus 1, x is less than or equal to negative 1. And we're going to do the same thing on the right. Multiply by 3. 2 times x plus 1 greater than or equal to, now 0 and negative 0 are the same, so times 3 is still 0. Divide by 2. X plus 1 is greater than or equal to 0. Subtract 1. X is greater than or equal to negative 1. So we have x is less than or equal to negative 1 and x is greater than or equal to negative 1. If we look at this on a number line, here's negative 1. X is less than or equal to negative 1 and x is greater than or equal to negative 1. Where do these overlap? Only at negative 1. So if I wanted to graph this, here's negative 1. I have just a closed circle. Okay. Now we're not going to use brackets to represent this because it would be difficult to see, but we can just represent our answer, x equals negative 1. We don't have to put it in a set because it's just one value. All right, in our next example, we're looking at an absolute value again, so we need to isolate it, and we can isolate it by adding 7 to both sides. So we have the absolute value of x over 3 minus 1 is greater than or equal to 2. Now I have my absolute value isolated. I can break it into our two cases. This one is a greater, so it's an or, great or. So I have x over 3 minus 1 greater than or equal to 2, or x over 3 minus 1 is less than or equal to negative 2. All right, now I want to solve each inequality individually. So plus 1, x over 3 greater than or equal to 3, times 3, x is greater than or equal to 9, or solving my second inequality, x over 3 is less than or equal to, add 1 to negative 2, I get negative 1, times 3, x is less than or equal to negative 3. What does this look like? If I have a number line here, here's my negative 3, here's my 9, x is greater than or equal to 9, goes out that way, x is less than or equal to negative 3, goes out this way. Now in or, I'm not looking for overlap, I'm looking for everything. So here on my final answer number line, I have negative 3, I have 9, and my answer is everything less than negative 3 as well as everything greater than 9. So interval notation would be negative infinity to negative 3 union 9 to infinity. And our last example here, we're isolating our absolute value first, minus 5 minus 5. Absolute value of 2x plus 9 is greater than negative 2. Now, can I have a distance greater than negative 2? Sure, all distances should be greater than negative 2, so I expect this to be for all real numbers. Let's take a look at what happens when I split my cases. It's a greater, so it's not an and, it's an or. Our first case, we have 2x plus 9 is greater than negative 2. Our second case, we have 2x plus 9 is less than, a negative of a negative is a positive 2. Solving our first case, Subtract 9 from both sides. 2x is greater than negative 11. Divide by 2. X is greater than negative 11 halves. Or subtract 9. 2x is greater than negative 7. Divide by 2. X is less than negative 7 halves. So when we graph this on a number line, we have negative 11 halves, which is smaller than negative 7 halves. X is greater than negative 11 halves or less than negative 7 halves. It's an or, so we're taking everything. Well, I have everything on the left, in the middle, and on the right. So our solution is all real numbers, just as we predicted. All right, make sure you write a conclusion sentence, and then you're done with the notes.